Hello students, in this part of work, energy and power, we will study about the energy. Capacity of doing work by a body is known as energy. The energy of a body is measured by the amount of work the body can perform. Therefore, like work, energy is a scalar quantity. The SI unit of energy is joule and is symbolically represented by J. CGS unit arc, and 1 joule equals to 10 raised to the power 7 arc. Different forms of energy. Energy has several forms: mechanical energy, heat energy, light energy, sound energy, chemical energy, electrical energy, internal energy, nuclear energy, etc. We will study mechanical energy in detail. The energy possessed by mechanical means is called mechanical energy. It is of two types: kinetic energy and potential energy. Kinetic energy is the energy of a body due to its motion. Means every moving body possesses kinetic energy. For example, a moving cricket ball possesses kinetic energy. A bullet fired from a gun can pierce a target due to its kinetic energy. The kinetic energy of air is used to run windmills, etc. Suppose a body of mass m moving with velocity u is acted upon by a force F for time t, and let v be the final velocity and s be the displacement at the end of this time interval. Then the work done will be equals to force into displacement. And by putting the value of force, that means mass into acceleration. And you know that by third equation of motion, v square is equals to u square plus 2as. And by calculating the value of as from this and putting in equation 1, you got work done will be equals to mass into half of v square minus u square. So the work done is possessed by the body in the form of kinetic energy. And if initially the body was at rest and the final velocity is v, then the kinetic energy will be equals to half mv square. Points to be noted: kinetic energy is directly proportional to mass of the body, directly proportional to square of the velocity of the body. So if you change the mass, say it is doubled, the kinetic energy is doubled. If it is halved, kinetic energy is halved. Similarly, if velocity is doubled, kinetic energy becomes 4 times because it is directly proportional to velocity square. Kinetic energy is always positive. As you know that mass is always positive and the square of the velocity will also be positive. Kinetic energy is a scalar quantity. Now, in terms of momentum, kinetic energy, you know, we have calculated half mv square, multiply and divided by m, you got half m square v square by m, and the m into v is the linear momentum. So kinetic energy will be equals to p square by 2m. This formula is very much used in the conceptual and numerical problems also. Now, work energy theorem. Work energy theorem states that work done by the net force acting on a body is equal to change produced in the kinetic energy of the body. Now, this one is the proof of work energy theorem for a constant force. Suppose a body of mass m moving with velocity u is acted upon by a force F and for time t, and v be the final velocity, and just calculate as we have calculated earlier. You will get work done will be equals to final kinetic energy minus initial kinetic energy. That means the work done is equals to change in its kinetic energy, and this one is work energy theorem. What about the work energy theorem for a variable force? Kinetic energy, you know, it is half mv square. Differentiated with respect to time, you got dk by dt is equals to d by dt of half mv square. Differentiated the d differentiation of v square with respect to dt, you will get 2v dv by dt, and half will be cancelled out and you will got mv dv by dt, or we can write it as m into dv by dt into v, and m dv by dt is force, so dk by dt is equals to force into dx by dt. Or you can say dk is equals to f into dx, integrating it within the limits xi to xf. When the initial position xi was there, the initial kinetic energy ki, and for the final position kf, the kinetic energy final is represented by kf. And the integration of dk will be k, and by putting the limit upper limit minus lower limit, you got kf minus ki equals to integration of xi to xf limits of f dx. So, and what is this one? Force into displacement within the limits of xi to xf, it will be the total work done. So work done is equals to kf minus ki. Or you can simply here integrate by just simply writing that force is equals to mass into acceleration, and you got m into dv by dt, and by putting in the value of work done, dw is equals to m into dv by dt into ds, means you got mv dv, and integrate it within the limits of initial to final velocity u to v, you will again get the same formula. You can adopt any of the method. A numerical problem. A woman pushes a trunk on a railway platform which has a rough surface. She applies a force of 100 Newton over a distance of 10 meters. Thereafter, she gets progressively tired and her applied force reduces linearly with distance to 50 Newton. The total distance through which the trunk has been moved is 20 meters. Plot the force applied by the woman and the frictional force, which is 50 Newton, and find out the work done by the two forces over 20 meters. The plot you can see in the diagram. At x is equals to 20 meters, the force is 50 Newton. And we are given that the magnitude of frictional force is 50 Newton. It opposes the motion and acts in the opposite direction. So the work done will be equals to the area under the graph, and that is the area of rectangle ABCD and area of trapezium CEID. And by putting all the values, you will get the work done equals to 1750 joule. And work done by the frictional force will be the area of the rectangle AG HI, and the value of the force is -50, and you will got -1000 joule.